Hello class. So the last part of the Laplace transform one that we are going to look at is the application of Laplace transform to differential system of equations. So in this case, you want to use your Laplace transform to solve differential equations, probably in their first order, second order, or third order. So how do that come to play? Now you recall that the initial transform itself, that is the Laplace transform, it's the L into the curly bracket f of t, and the transform is the capital F and S. So for the first order differential equation of this, if the function of time in this case is being differentiated for the first time, the Laplace transform is the s f of s minus f, and the time is 0. That's why you have 0 inside of this bracket here, and your time t is 0. Now, for the second derivative of the function of time, the Laplace expression is this. These are standard expressions, so they are standard. And for the third order differential for the function of time, to get a Laplace equivalent, the transform is this. And for the fourth, you can just evaluate that from here. For the fourth, it will be s raised to power 4 f of s minus s cubed f into 0 minus s squared f into 0 minus f 3 f0 minus f2 f0. So that will be the fourth order for the Laplace equivalent of the fourth order differential of the function of time. But here we're just talking at the third order, and the Laplace expression is what is being given here. So for instance, the function of time in this case, that's f of t, which is the function of, let me just erase this. So the function of time is x. So at time equals to 0, it is given that x is same as x naught. So this one can be written as the function of time, because time is said to be 0, equals to x naught. Because we are told that, okay, the function of time equals x, and at time equals to 0, x equals to x naught. So if you are putting f and replacing the time with 0, definitely that will equal to x naught. So if you differentiate x with respect to time, that's dx dt, you have x1. So dx dt is the same thing as saying you have, so you're saying if you are differentiating x with respect to time, dx dt, the output is x1. So this is the same thing as saying x dot equals x1. So if you are doing the second differential of this, that will be d squared x over the t squared. This is x2, and this is the same thing as saying your x double dot is x2. So that is just what you have here. So we are differentiating x the second time, you are having x2, the third time x3, up until the nth term. So that's dn x over dtn, and that will be xn. So for all function of time at time equals to 0, so there will be x1, x2, x3, xn. So the x, the t, the same thing as saying you have your x dot, saying you have x dot, and second differential of your x is the same thing as having your x double dot equals x2. So it's just another notation of your dx dt saying the first order of x, second order, third order, fourth order, or up until the nth order of n. So the Laplace equivalent of x now is what is being given here. So just saying that the Laplace for, let me rub all of this. So the Laplace for x is x bar, just what we have here. That's what we have here. And that of the first derivative of x, that's x dot. So it's your s x bar minus x naught, just what is being written here. So these are standards, like I said. So they'll be used in the first order differential equation, solving them with Laplace transform. So this for the second derivative of x, and this is for the third. So these are the equivalent transforms of these differentials of x. Now, the procedure for using Laplace to solve first order differential equation is that, number one, you need to write the equation in the Laplace form. Then you'll be given initial conditions. So after you rewrite the equation in Laplace form, then you insert the initial conditions. Then after then you rearrange the equation. The goal is you want to make x bar the subject. You want to make x bar the subject so that you can solve the Laplace problem. So that is why you need to rearrange. You rearrange, then you make x bar the subject. Then after you have made x bar the subject, then you find the inverse, just like we did in Laplace inverse transform. So you find the inverse. Now, given this first example, we are told to solve the differential equation using Laplace transform. Now, here we are given the equation. This is the equation here. And we are given the initial condition here. Now, we are told that the first differential of x, that's x dot, minus 4x equals 8. At t equals 0, then x equals 2. Now, the Laplace equivalent of all of this is what we are going to first of all find. And we know that from here, the Laplace transform of our first derivative of x is equivalent to x bar minus x naught. That's the equivalent. So that means to rewrite this in Laplace form, this x naught will be replaced with this. Now for x, we know that Laplace transform for x is x bar. So that means this x here will be replaced by x bar. And we know that from the standard transform, we know that a constant, the transform is that constant over s. That is what we have here. So the first step, like I said, is to rewrite the equation in Laplace form. So, and we have the equation here. And we know that the transform for the first derivative of x is x bar minus x naught, which is this. And the transform for x is x bar. And we know that for a constant from our standard transform that we have already, we know that that transform for a constant is the constant divided by s, which is what we have here. So to rewrite all of this, we just plug in this back into this equation. So replacing x dot with x bar minus x naught, and replacing x with x bar, so that makes 4x bar. Then replacing 8 with the Laplace equivalent, which is the 8 over s. So this is the Laplace form of the equation. So with that, we are done with this first process of rewriting the equation in Laplace form. So all we did first is to convert each of the elements of the equation into the Laplace form, and then plug everything back into the equation. Now, please don't make the mistake of changing 4, because 4 is 4x, not just 4. So that you make the mistake of changing 4 again into a constant transform of Laplace. So you will be having something like 4 over s, then x bar. No, you are only taking the x factor in this case. It's only here when you have a constant or you have another form of any value that does not have x that you can take the transform directly from the Laplace table. So for instance, if this is sine whatever, you can take the Laplace from the transform table that we have. But in the case whereby you are having a value and the x, it's only the x term that you'll be converting into the Laplace equivalent for this differential solution with Laplace, so that that mistake will not cause problems along the way. So rewriting the equation in Laplace, we have done that here, converting the x dot, the first derivative of x, into the Laplace equivalent, and the x to the Laplace equivalent here also, and the constant term, which is 8, into the Laplace equivalent here. Now the next thing is for us to insert the initial conditions. Now the initial conditions, we know we are given at time t equals to 0, x equals to 2. Now if we look at this equation, we don't have x there, but we know that from here we know that our x at time t equals to 0 is the same thing as x naught, and x dot is x1, x double dot is x2, x triple dot is x3. So at time t equals to 0, x is equal to x naught, x dot is x1, x double dot is x2, and on like that. So that is how we are going to insert the initial conditions here, because you might be wondering, okay, how do I know where to put my 2 now? So that's why I did it here, that x equals to 2 equals to x naught. Where I got this from is from here. It's from here that at time t equals to 0, x equals to x naught. And at time t equals to 0 also, x dot is x1, x double dot is x2, x triple dot is x3. So that is how you are going to put in the initial conditions, because when you check from the question itself, it was only given as x. So before you know that your x is the same thing as x naught at time t equals to 0, and so on like that. So replacing x naught now with 2 is what we have here. So s x bar minus 2 minus 4 x bar equal 8 over s. Now the main thing about the rearrangement is to work around all of this and make x bar the subject. So the first thing that was done is to bring this constant minus 2 to the right side of the equality sign, which makes it positive 2. And if you take the math here, doing the LCM of s for both denominator, you have 2 multiplied by s plus 8, which is this, what you have here, which is all of this. Then you still have your s minus s x bar minus 4 bar x bar here. So to make x bar the subject is what has been done here. You bring x bar out, you have s minus 4x into bracket equals 8 plus 2s over s. So just from here, making x bar the subject, because x bar is what we are solving for. So for the solving a differential equation with Laplace, is the x bar that I want to solve for. It's the x bar that I want to find the inverse, because from here we know that it's the inverse of this x bar that will give us the Laplace form of x. So we have here x bar, and we can make x bar the subject by just saying, bringing s minus s4 as the denominator here, which is what has been done here. So with this, we have made our x bar the subject here. So I haven't made x bar the subject. The next thing is to find the inverse of this problem that you have here. So the inverse of 8 plus 2s divided by s into s minus 4. So the inverse of this will give us the x itself, because from here we know that the Laplace of x that gives us x bar. So when you take the inverse of x bar, you have x. So just the way we worked around it when we're solving for inverse. So again, we are going to be using the the partial fraction again. So we have denominator of s and that of s minus 4. So a is taking the denominator for s and b is taking that of s minus 4. So if we do the partial fraction like we did the other time when we are talking about the inverse, so a is having this and b is having bs. So that's what you have here. So the next thing is to find a way to turn either this to 0, s minus 4, or s to 0 and solve for b or solve for a, as the case may be. So when you make s to be 4, so if you put 4 here, that will be 4 minus 4 will be 0. So the whole of a will go out because a is multiplying this bracket of s minus 4. So that means when you put 4 as a value of s, you have 4 minus 4 is 0. Then a multiplied by 0 will be cancelled. So you have here bs, which is b4 now because the value of s has been changed to 4. So you have 8 plus 2s here, which will be changed to 8 plus 2 into 4. And 2 times 4 is 8. So 8 plus 8 will be 16 equals bs. So what I'm just trying to explain there is saying we have when s is given the value of 4 and we have 8 plus 2s equals 4b because sorry, let me still put this as bs, and we know that the value of s is 4. So now this equation becomes 8 plus 2 into 4 equals 4b. So that means 8 plus 8 will be 16. So 8 plus 8 will be 16. So that will be 8 plus 8 equals 4b. So if you 16 divided by 4 will give us b equals to 4. So b equals to 4, and that's how we got our b here to be 4. Also, if we go back to this same equation and make s to be 0, we'll make s to be 0 here. So b will cancel out. So we are left with 0 minus 4. So that will be minus a. Then 2 times 0 will be 0. So that will be 8 equals a minus 4a. Just saying this. Saying we have, for the second time, we are saying s is given the value of 0. Given the value of 0. S is given the value of 0. And the equation itself is 8 plus 2s equals a into s minus 4 plus bs. So when s equals to 0, the bs will cancel. So we are left with 8 plus 2 into 0 and a into 0 minus 4. 0 minus 4. So here we'll be left with 8 equals minus 4a. So minus 4a now. So a will be equal to minus 2. Equal to minus 2. So that will be the value for a. We'll check here now. So that's why we have a as minus 2 here. Now that we know those two, we just need to put them back into this expression. Because now, all of this is equivalent to this. To all of this. So that would be a is minus 2 and b is 4. So that would be minus 2 over s plus 4 over s plus 4. We can equally rearrange this and say 4 over s plus 4. Sorry, this is minus over s minus 4 over s minus 4 minus 2 over s. Now, if we go back to our table, we know that this 4 over s will only be 4 into 1 over s into 1 over s minus 4. 1 over s minus 4. And this is the same thing as 4, because from the standard, 1 over s minus 4 is the same thing as e 4t, because a here is 4. If you go back to the table, you see that 1 over s minus a is same thing as e at, and the a here is 4. So 4, this 4 here multiplying the e 4t. So that's the transform of this. And we know that 2 over s, this is just an equivalent, a constant. So that means it's 2. Because from the table, we know that any constant over s, the inverse of that is that constant itself. So that will be 4 et minus 2. So that is the inverse, which is what we have here. So which is what we have here. Let me just run through it again. So to solve differential equations with Laplace transform, you rewrite the equation itself in Laplace form. You insert the given initial conditions. Then you rearrange the equation just to make x bar the subject. Then you determine the inverse. Now, given this example, x dot minus 4x equals 8. Now, we know that this is the first derivative of x. And when we go to our standard, which is what we have discussed here, we know that our x dot, the Laplace form of it, the transform of it is s bar minus x dot. So, which is this. And for x is x bar. And for a constant is that constant over s from the standard transform table that we have before. This is where we got this from. Now, and I said again that you don't make the mistake of transforming this 4 as a constant itself, because it's having the x factor in this case. So for the first, for differential equation with Laplace, you consider the x term. Now, you only use the standard table for factors that does not have the x term. That is why it's only the 8 that we look up from the standard table. This 4x that has the x term is only the x that we transformed into x bar. And for the x dot, we know that that is the first derivative of x, which is this. So if we plug all of this back into the equation, we have this. Now, we are given initial conditions at t equals to 0, x equals to 2. Now, also we know that from here, at time t equals to 0, my x equals to x naught. And at time t equals to 0, my x dot is x1. At time t equals to 0, my x double dot is equals to x2. My x triple dot is equals to x3. So the initial condition I'm giving is that at x equals to 0, at t equals to 0, x equals to 2. And I know that at my time t equals to 0, my x is the same thing as my x naught, which is what has been written here. So putting this initial condition into this equation is what has been done here. The x naught now is 2 here. Now, what is left is to rearrange the equation until we can have x bar as the subject. So the first thing that was done here is to bring this minus 2 to the right side of the equality sign. So that will be 8 over s plus 2. And if you take the math of this, you know that for s having to be the denominator, 2 times s plus 8 has to be here as the numerator. And also, from here now, you can make x bar, factor out x bar here to have this s minus 4 in the bracket. Now, to make x bar the subject, we only need to bring this bracket of s minus 4 as the denominator on the right side, which is what has been done here. So what is left is to find the inverse because finding the inverse of x bar will give us x, which is our solution. So we're going to find the inverse of this right-hand side. So using the same analogy of inverse that we talked about before, which is the partial fraction. So we have two denominators here, s and the s minus 4. So a over s plus b over s minus 4. And when we do the partial fraction mathematics here, a will take the denominator of this and b will take the denominator of a, which is what has been done here. And this will be cancelled. Denominator here will be cancelled. Now to find a and b is the necessary evaluation that needs to be done in the partial fraction. And to do that, to find a way to turn all of this to 0 and find b, or turn this to 0 and find a. So when we say when we make the value of s to be 4, so putting 4 into here, will be 4 minus 4 will be 0. So that means at that point a will go and I've left b. So if we put s equals to 4 in all of this, we're going to have 8 plus 2 into 4. And also, this will cancel out, and also b into 4. That will be 4b, then a plus 2 into 4, which is what we have here. Then if you do the math here, you have b equals to 4. And the other time, again, to find my a, if we make s to be 0, making s 0 will cancel out b. So we are left with 0 minus 4 and 2 times 0. So that's why we have a, 8 equals minus 4a, which is what we have here. So, and we'll just do the necessary evaluation here. We know that we have a to be minus 2. So going back here, making the a value that we have had, replacing them here, that will be minus 2 over s plus 4 over s minus 4. Now we know the next thing is to find the inverse of this, which is what has been expressed here. So finding the inverse of this will give us our x, which is our solution. Now, we know that s minus 4 by s minus 4 can only come from an exponential term. So that will be 4 times e raised to power 40, which is what was done here. So 1 over s minus 4. This is an exponential term in the function of time. So the inverse of this is e40. So that will be 4 multiplying the e40. Then this is a constant itself, 2 over s. So any constant over s in the standard table of Laplace is that the inverse will be the constant, so which is 2. So that's why we have the solution here as 4e40 minus 2. So the second example here is what is being shown. We are given that x double dot minus 6x dot plus 8x equals e3t. And at time t equals 0, we have x equals to 0 and x dot equals to 2. Now, the same way, the first thing is to rewrite the equation in Laplace form. So what is the Laplace of all the x term? So the x double dot from here, which is what is here. For the x double dot, we know that the transform is x squared x bar minus s x naught minus x1, which is what has been done here. This is what has been done here. And for x naught, this is the equivalent in Laplace, this is Laplace expression for it. And for x is x bar. Then the e3t will be gotten from the standard Laplace table, which is 1 over s minus 3. That is where this one came from. So putting all of this back into this equation. So all of this will go for x double dot, all of this will go for x dot, and all of this will go for x bar, and this will go for e3t, which is what has been done here. So the next thing, our initial conditions at time t equals to 0, we know that x is the same thing as x naught, which is equals to 0, and we know that x dot at time t equals to 0 for the initial condition is the same thing as x1. So x1 equals to 2. So that is what has been put here. At time t equals to 0, x equals to 0, which is the same thing as x naught, and x dot equals to 2 which is the same thing as x1. So what will happen is to insert all of these initial conditions now into this expression that we have here, which is what has been done here. So now we know that my x0 is 0. So if x0 is 0, this will go, then x1 is 2. So this will be 2. So that is what we have here, because x0 is 0. So x0 has been taken out and x0 has been taken out. So that's why we have s squared x bar minus 2, because my x1 is 2. This is x1. So minus 2, then 6 x bar, because 6 has opened this bracket here. However, our x0 is 0. So that has been removed. So we have all of this. We have this now. So the same way, we bring the constant term to the right side. So the denominator here is shared. That will be 2 multiplying this. That will be 2s minus 6, which is this numerator here. So that's what we have here. Then making x bar the subject. So that will be x squared, 6s, then 8. And you can make x bar the subject here by bringing all of this as the denominator here. But you can also factorize this. The factor of this using factorization is s minus 2 and s minus 4. Because if you do the multiplication of these two brackets, you have s times x will give you s squared, minus 2 times minus s will give minus 2s, s times minus 4 will give minus 4s, so minus 4s minus 2s will give minus 6s, and 2 times 4 will give plus 8, minus 4 minus 2 multiplying themselves will give plus 8. So the factor of this is this, and from there we can use the partial fraction a, b, and c to take each of the denominators like has been done here. So when we cross multiply, a will have these two denominators, b will have s minus 3 and s minus 4, and c will have s minus 2 and s minus 3, which is what has been done here for the partial fraction. So the next thing is to find a way to turn all of this to 0 so that we can find possibly C or B, then turn all of this to 0 again to find A or other coefficients of the partial fraction. So when we make our S to be 2, in this case, if S is 2, S becoming 2 here will mean 2 minus 2 will be 0. So all of this will be cancelled. And S becoming 2 here again will be 2 minus 2, 0. So all of this will be cancelled. So we are left with B. So 2 minus 3 will be minus 1. And 2 minus 4 will be minus 2. So minus 1 times minus 2, that will be plus 2. So that will be 2b, which is what we have here. Then putting 2 here, 2 times 2 will be 4. 4 minus 5 will be minus 1. So at the end of the day, b will be minus 1 over 2. That is how this one came to be. Then, having gotten that, if we make s to be 3, so putting s to be 3 will be into this equation, taking this equation again. So s being 3, 3 minus 3 will be 0. So all of this will be taken out. Also 3 minus 3 will be 0. All of this will be taken out. We are left with A. So 3 minus 2 will be positive 1. And 3 minus 4 will be negative 1. So minus 1 times plus 1 will be minus 1. That will be minus A. And 2 into 3 will be 6 minus 5. So that will be positive 1. So 6 minus 5 is 1 equals minus A. So that will be A equals to minus 1. So when we make our S to be 4, we'll go back to this same equation, making S to be 4. So 4 minus 4 will be 0. It will cancel out this. 4 minus 4 again will be 0. It will cancel out the V factor. And we're left with C. So 4 minus 3 will be 1. Then 4 minus 2 will be 2. So that will be 2 times 1 is 2. So that's 2c. Then 2 times 4 will be 8 minus 5. So that's what we have here. So 2c, 8 minus 5, that will be 3 equals 2c. So that will be c is 3 over 2. So now we have all the variables for the partial fraction. We have the a, which is minus 1. We have the b, which is minus 1 over 2. And we have the c, which is 3 over 2. So just taking the minus, to the back. So we have 3 over 2. This is the c factor of the partial fraction. This is the b factor, and this is the a factor. So we recall that b is minus 1 over 2 and c is 3 over 2 and a is minus 1. So this is just a rearrangement. Now from the table also we know that 1 over s minus 3 can only be e raised to power 3t, which is this. And we know that 1 over 2 s minus 2. 1 over s minus 2 can only be e raised to power 2t. So multiplying it by minus 1 over 2. That is what we have here. So we are taking the inverse now at this point. So 3 over 2 into s minus 4. We know that this can only be 3 over 2 times 1 over s minus 4. So and 1 over s minus 4 is e minus 4t. So that is why we have e minus 4t, 3 over 2 here. And this is the transform of this inverse. This is the inverse of this transform, and which is our x bar, which is our x now, because the inverse of x bar is x, so which is our x, and that is the solution for the second example, which is the second derivative of x in this case. Thank you very much.